yesterday I noticed, during the afternoon, these exercises on the machine. It was really absurd. It was really absurd to try to have you input the WX notation and and Pretty was spelling WX. I mean, this did not make any sense at all. Then we understood that you were not familiar with the transliterations, and so maybe it's a good time to say a few things about transliteration, romanization, transmission of information, and so the next two courses will be about this topic. I will start with very simple, easy things, and then Peter will follow because he has studied this problem very consistently. He has written a book about it, so he will add details. I will start with very simple ideas about what information is. See, you're teachers yourself, so you have to transmit knowledge to your students. And here it's the same, we are the teachers and we have to transmit knowledge to you. So you get knowledge because we transmit information. Okay? And so how do we transmit information? We transmit information between humans, mostly by language. I mean, first, it's by gestures, yes, or shouts. I'm angry at you, so I will shout, and I will hit you, or whatever, yes. So this is how animals communicate, yes. But as humans, we have this wonderful faculty of language, in which we can encode information and transmit information and teach using language. So when we teach, we do gestures and these kind of things, and we can raise our voice more or less. So some information is transmitted there, but mostly it's through language. And then we are using the machines. So the machines also, they are manipulating information, but it's information of somehow different nature. So the purpose of the course is to explain how, to a certain extent, we can manipulate linguistic information with the machine. Okay? But it's not obvious at all that the information that we manipulate with our machines is the same kind of information that we are transmitting when we are speaking. Okay? So there is a little bit of mystery here. And this mystery was explained by an American scientist called Shannon, who started a new scientific field of study called information theory. And information theory is something very important for the design of digital computers and the design of data structures in our programming languages, and so on and so forth. But it's more general, a theory of information and how you transmit information through channels. Channels, like, you're talking on the telephone, so it's a channel. So what is information? What is the unit of information? Unit, like here, this is a monetary unit. It's 1 rupee. Okay? It's a monetary unit. Is it a unit of information? Yes, in some sense. It has two faces. Okay, so I can transmit information to you by showing you one face or the other. It's called heads and tails. Okay, so it's some kind of minimum information. So I can flip a coin, yes, and when the coin is flipping, there is no information. We say it's random. Okay, so when we want to make some kind of, equal share or whatever, yes, we say, okay, we'll draw between us, okay? And then we flip the coin. And when the coin is turning, then it's random. We don't know how it will come out. When it comes to your hand, now you have exactly one rupee, but you have also exactly one bit of information. So it's called a bit. Then you have crossroads where you have two possibilities. Yes, you can go left or you can go right. Okay, and by a sequence of bits, then you can tell where to get the treasure, where to get the knowledge. Okay? So that's at the bottom of information. And then you can develop all the notions of computer science in order to tell how information is stored, manipulated, and so on, using these basic concepts. Now, what about language? This information transmitting between humans. As I said, the main communication channel is language. So where are the bits in language? Okay, so in a sense, this is the purpose of this week workshop, is to understand how, by packing information this way and that way and that way, then we get some linguistic units, and more linguistic information, and more, and then we go from basic things about speech to higher level information, higher level knowledge in a general sense. Okay, so linguistics is the study of how information is encoded in linguistic units. Okay, so the first level is a level of speech. Okay, so we transmit speech, and here it's a little bit more sophisticated than going left or going right. It would be very awkward to speak between ourselves by saying heads, tails, or 0, 1. This is good for computers to transmit information like that. But we have our brain that is able to process more, and so we can process shabda. Okay, so the first level in speech, shabda, and so these are letters encoded phonetically. So there is a field of study which is called phonetics, and phonetics is the study of what is our human organs for speech, with the mouth, with the navel cavity, with the larynx, with the vocal cords, with all this, the variations you can make. And so this is the emitting part, that goes in the channel. The channel is just a vibration of the air, yes, or encoded on the telephone line. But it's basically these basic vibrations. And then at the receiving end, then we have the auditory system. The ear is able to differentiate some of these sounds, and so we recognize what the other one is speaking. Okay. But it's rather complex, these air vibration rates, so it's a mixture of physics and of physiology. Yes, but it's basically a continuum medium. Yes, there is some kind of a continuum between T and D, for instance. You know, between T and D, what happens? You know, your organs, you open. D is voiced, and T is not. Okay, so it's but it can be more or less voiced, or like the difference between T and T, where you emit some expiration, which may be more or less pronounced. Okay, so somewhere we have to map all these phonetic variations, which are continuous, into a more discrete medium where we can discriminate. Oh, you said T, or you said T. Okay, so it's discrimination.
I will translate some of these technical terms in Sanskrit. The hoist. You use the word hoist. Okay?
Yeah, voice is T versus D. We don't need to go into technicalities really. It's
the corresponding terminology in Sanskrit.
Please, madam.
So what is hoist? Do you know? You have Ghosha, Aghosha, Mahaprana, Alpaprana. Okay? So one is hoist and aspirated. Okay? So Mahaprana, Alpaprana, this is aspirated and aspirated. And hoist is Ghosha, and hoist is Aghosha. Okay?
Thank you. So here, these notions, I mean, thank you, madam, for telling about Sanskrit, yes? But I was not speaking about Sanskrit.
No, not telling about the Sanskrit. They are familiar with these words. They are not familiar with what is voiced. Therefore, I just translated
Yes. But for instance, there is a difference between dental and cerebral. Okay, so this is dental and this is cerebral. Okay, so this is Mordanya and this is dental. So here the difference is in the movement of your tongue. Your tongue may be back in the palate or go forth to the teeth. So this is the variation between the varnas. Yes, you have 5 varnas. Okay, so this tradition was started in Sanskrit long time ago. So it's recorded in, in the beginning of Ashtadhyayi, Pratyaharas, and some, this nice table of the kind of official Sanskrit sounds, okay, and which are very neatly organized. So old-time grammarians, of them, Panini was one, but he was probably not the first, there was a whole tradition. They analyzed very precisely this phenomenon of sound transmission and how you can distinguish carefully between various sounds so that you get a notion of Shabda, which is discrete. This is an important point. That phonetics, it's continuous. It's about, moving more or less the tongue, opening more or less this cavity, and so on. Whereas Shabda, so in Western terms, this is called phonemics. So you should not confuse phonetics and phonemics. Phonetics is continuous, and phonemics is discrete. So it tells in what way sounds are differentiated essentially. Okay, and sounds are differentiated essentially. It's mostly a cultural thing that is attached to one particular language. It is not something universal. See? Phonetics is universal. because we are all alike. Yes, we have the same possibilities of speaking, hearing. But phonemics, what are the units of information transmitted with sabda, is depend on the language. Okay? For instance, in Tamil, it's very hard to use Tamil for encoding Sanskrit. Yes, because in Tamil, they will not distinguish between the various dentals, for instance. Okay, so.
For example, in Tamil, you have tha, tha is represented by only single symbol. Only one symbol represents all tha, the first four varnas. Similarly, for ka, kha, ga, kha, only one letter.
So there are sounds that are differentiated by certain people, certain languages, and not differentiated by other people speaking other languages. For instance, in Sanskrit, you have V and B. Yes? Vija, bija, this is not the same. But in Bengali, it's the same. Okay, so in Bengali, you don't distinguish between B and V. Okay, so you cannot use Bengali directly to encode Sanskrit because of that, in the same way that you cannot use Tamil directly. Whereas Malayalam is much closer. You have more distinctions, so it's easier to transmit Sanskrit in Malayalam. See, so this is cultural. This is attached to the language. And the criterion for two shabdas to be essentially different is that they will help you to discriminate at the next level. The next level of information after sabda is pada. Okay, so certain padas are differentiated because they are all the same except for one letter. Okay, and this difference of one letter is essential so that you can distinguish the two padas. Okay? So for instance, in Sanskrit, the phoneme A is distinct from phoneme E. There are two different vowels. Yes? Because you have Shiva and you have Shava. Okay, and these are essential different words. Okay, so Shava and Shiva tell you, oh, A and E have this differentiating power. So there are different phonemes. And so in the Sanskrit alphabet, there are different shabda. Okay, so this is absolutely essential, and it's absolutely wonderful that that Panini had all these concepts clearly organized. You know, in Western linguistics, and if you look in a standard book on linguistics, you will find that phonemics was invented by this Polish linguist in the 19th century. Yes. But it's clearly a part of the Sanskrit heritage of back to Panini. Okay, and similarly distinction between B and V. See, if you want money, if you want more rupees, yes, you pray for Kuber, or you pray for couvert. Okay, so there are languages where you must say couvert or you must say couvert, but in Bengali it's the same. Couvert, couvert, same. Okay, so B and V are not essential to discriminate words in Bengali, so they are in the same space. Okay? So the big phonetic space is cut into pieces. And these are the phonemes, the shabda. Okay. So in Sanskrit we have what 48, 49, of the order of 50 such shabda, and they are enough to distinguish the padas, the next level of information, these words. Yes, and so you can think of Sanskrit as encoding information first in shabda, in units of information, which is having your choice between 50 possibilities, as opposed to the elementary unit of choosing between two possibilities. Okay, so you get more information out of one phoneme, because you are discriminating between 50 choices, rather than flipping a coin, where you can discriminate only between two. Okay, so this is why we need more bits to encode the letters. Okay, so this problem was recognized very early in the design of computers. Yes, because computers in the beginning, they were used first as computing machines. So they had arithmetic units and so on, so that you could make additions, and so the banks could do business, take your money and make some addition, then make some subtraction from your pocket. Okay, so yes, this is why it developed. Science develops mostly because of money and because of weapons. Okay, these are the two driving forces for technology. Hopefully there are people who are seeking knowledge, and seeking knowledge is a real motivation for science. Anyway, let us not get distracted on these topics. But in the beginning, you had these computers that were making, crunching numbers, and then you had other computers that were, doing listings and manipulating basically language. Okay, and these machines were really different. You had, so IBM Corporation was working on the information processing, and UNIVAC control data were working for the scientists making computations in the banks and so on. And then it was realized that this was duplication, actually the same notion of information and so on. So the computer words, the sequence of bits, can be used to represent numbers, or they can be used to represent letters. So there was some initial confusion of how many letters should you, how many bits should you pack in order to represent one letter, for instance. For integers, it's a different matter, see, because it's not finite. So you have to have some convention of, small integers, bigger integers, and so it's more complicated. But for text, it's letters, and so people work on some codes that would encode letters in so many bits. Okay. So the unit of information after the bit is called the byte. And the byte traditionally is what is needed to represent one letter. And a byte is obtained by 8 bits. Okay, so you write 8, either 0 or 1. Okay, so now instead of choosing between two possibilities, you're choosing between 64 possibilities. Okay? 256. 256, thank you, madam. 256 possibilities. So you can encode letters and then some control character and this and that, okay? And you have lowercase letters and uppercase letters and so on. Why? Because all this was done mostly in Western countries and in Anglo-Saxon language, and so the letters were the letters from the English alphabet. Okay, so you need 26 or so and then the uppercase, whatever. But please. Okay.
Any questions? Is it okay?
Okay, so remember, this byte is you have to choose with so many, and it corresponds to 8 bits. Or you can think, byte is like byte is written B-Y-T-E, yes, but it's pronounced the same as byte, yes, as byte B-I-T-E, yeah, half byte. Because this is the way computers crunch text, 1 byte at a time. And then you realize, but byte and byte are 2 different words. It's written differently, but it's pronounced the same way. So it's wrong encoding. Okay, yes. So it's very hard to read English. Yes, I refer to the talk of yesterday. Yes, you have all this. And French is still worse. So these languages are very imperfect in encoding speech into a written representation with letters. Okay, so here we are coming to a different tradition. See, language is shabda. This is speech, and it's encoded with varnas. Thank you, madam. Whereas the written representation is some kind of convention that we shall use a certain graphical representation to represent a phoneme. Okay, and it's a pure convention. And it's imperfect because languages change. Okay, so the encoding of English into the Roman alphabet must have been adequate at some point in history. Yes, but it got frozen there, I don't know, in the 8th century or 10th century or whatever. And then the language changed, and now the sounds don't correspond, not match to the written representation anymore. Yes. Whereas in Sanskrit, when the language was written, yes, then there was a careful choice of letters, written representation, like Devanagari, that would represent in a one-to-one correspondence a certain image with a certain sound. Okay? And since Sanskrit was very well defined by Pananis, Ashtadhyayi, by Trimuni, and so on, it tended not to change that much. It changed a little bit, yes, but not that much. And so this is why Devanagari is still perfect to represent the Sanskrit sound. Okay, so it's a rather perfect encoding of the sound, which is not the case for English or French with Romanization. Okay, so these are generalities, and it's all very simple, but you must have these ideas very clear in your mind in order to understand them and in order to teach them yourself. Yes, all these distinctions. So now we come to computers, and in computers we, first there is printing. This writing came about when people wanted to transmit information at a longer distance than at a voice distance. Yeah? So if you're, you're a merchant, you're selling some goods. Okay, so you want to write on the parcel, what is the good inside the parcel, so that at the receiving end, maybe very far away, it's been traveling by camel all through Middle East and so on, and so you know what. So it's for memory reason, also, because sound that is transmitted only orally, it means the knowledge relies on your memory. Okay, so this is so before writing, there was a need of memorizing enormous text, like memorizing Ashtadhyayi. This is one of the reasons of complexity of Ashtadhyayi, by the way, yes, is that it's very compact because Panini was very much aware of these information theoretical notions. So he knew that in order to transmit well the language, he had to give a lot of information, and this information was hard to get in the memory of ordinary people. So you had to develop special skills for memorizing all this, okay? So at some point, writing was needed for these two reasons, for transmitting information far away, and for storing lots of information on some concrete medium like stone or paper or palm leaves or whatever, that would not need human memorization that much. Then came computers, and then you have to decide what you put as information in your computers. So if we put Shabda, it's very complicated, yes, because of course we know to record the sound, yes, but these wave patterns, they take lots of space and so on. And then you have to analyze them and so on. So even nowadays with modern technology, this is not fully developed. This is called speech processing. Okay, so it's coming. It's coming. In a matter of 10, 20 years, there will not be keyboards anymore. We shall speak to the machines. Okay, so keyboards and all this is kind of transitory technology. But for the moment, and from the beginning of computers, we had to encode not the sound, but the writings. Okay, so now we are accumulating difficulty, okay, because we have the encoding of sound in writing and then the encoding of writing in bits in the computer and so on. So this was solved more or less for the Roman alphabet with a byte. And so in a byte we know to recognize A, B, C, D, and so on. When you go to Sanskrit, then you have to understand how to get these encodings. And encoding like Devanagari, for instance, if you want to print Devanagari by computer, then you need some kind of sophisticated technology. Or if you want to recognize Devanagari and so on. And so at some point, like in the 19th century, when lots of Westerners were interested into understanding Sanskrit and the Sanskrit scriptures and so on, they had to use the technology of the time to represent the Sanskrit words, the Sanskrit sentences, and so on. Okay? So in the 19th century, they decided to normalize some kind of representation of the Sanskrit alphabet in terms of Roman alphabet. Okay, and this is what is called Romanization. So Sanskrit Romanization is how, now we know that we can, for the Sanskrit side, we can talk in terms of Shabda or in terms of Lipi, the same, because it's, there is this perfect correspondence between the letters of the Devanagari alphabet and the sounds. But now, in order to encode them into the Roman alphabet, then we have to do something. And there is some fine-grained distinction between T, 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 that we cannot use T for both. You know, this is the same kind of problem that you get if you want to represent Devanagari in Tamil, Sanskrit in Tamil. Yes, you don't have enough of those. So it was coined some kind of little modifications of the Roman alphabet letters, yes, that are called diacritics. Diacritics are some marks that you put around, like here. There's dot under the T. There's dot under the R to make ri. There's dot under the S to make sh. Or you can use two letters, for instance, for expiration. You write ch as T, then H. Okay, so you use two letters to encode one shabda. Okay? And it's not about akshara. One varna. So it's not a perfect encoding. It's imperfect from the information theoretical point of view. Yes, because remember, now this Roman letter is encoded inside a byte in some kind of convention called Ascii. Okay, so Ascii is a convention for encoding letters into bytes. So here we use one Ascii letter, here we use two, and here we are stuck. Okay, this is not part of the Ascii convention of representing Roman alphabet into bytes. Okay, so we have to do something else. So this convention of using certain combinations of letters plus certain diacritics, this is called Romanization, and it is more or less standard. Okay, this was standardized in the 19th century, and minor, very small discrepancies, it's standardized. So you can read all this Indological work that refer to Sanskrit, so you have some kind of melange, of mixture of English and Sanskrit, with something that looks like the Roman alphabet with some difference. By the way, these diacritics are used also in Devanagari, for instance, for the in Hindi, for the Z sound, which is not in Sanskrit.
For sounds, we use these dots.
Yeah. So it's the same idea, it's the diacritics. Okay. So Romanization was standard for books. Okay, Indology books typically, you know, where you want to speak about Sanskrit in English or in French or in German. Okay, so this is more or less fixed. But at some point, when computers came, then we had to represent Sanskrit in some other way. So the first period is the Ascii period. So from 1945 till now, and it will continue forever, but it's an encoding of characters in bytes. Okay? And so how do you translate Romanization into Ascii? This is what is called transliteration. Okay? For transliteration, you don't have any diacritics anymore. You cannot write this dot. You have to encode this into some notation using the letters from the Ascii alphabet so that you can type it on the keyboard. The keyboard corresponds to this notion of Ascii. So you have transliteration, and then it's a bit unfortunate, but there is no standard of transliteration. Amba, please could you put the projector on my slide, because this is the time of showing this. Okay, so basically, so now you have many transliteration schemes. It's a little bit confusing, so apologies for this confusion. It's all this will vanish at some point. It will vanish when we shall go into the next stage, which is called Unicode, where you represent information in bigger chunks than bytes. Okay? So this I will leave to Peter to describe this further level. Yes? So in the future this problem will vanish, but today we are using transliteration for communicating with our machines to our Sanskrit platforms. And unfortunately, Madam, Ambaji, Peterji, myself, we use 3 different transliteration schemes. Okay, so I understand the confusion in the class, and we deeply apologize for the confusion. So this is the intent of this lecture, is to dispel a little bit of the confusion and to explain why we are in this situation. Okay? So I say basically we have 2 families of transliteration schemes. One is 1-1, and one is many-1. What do I mean? 1-1 is that one ASCII letter, one keyboard stroke, is equivalent exactly to one Sanskrit phoneme. The other one is that in order to get one Sanskrit phoneme, you may have several keystrokes. Okay. So the 1-1 transliterations are called wax and sloppy. I mean, that's not what their authors call them. They call them WX and SLP1. Okay? And here on the chart that will appear, we shall witness that it's indeed 1-to-1. The many-1 schemes, there are 2. One is called, I call it the VH, and actually it goes back to some Dutch scientist called Veltuis, who designed a scheme in order to represent Sanskrit text in a computer processing program called TeX. Okay, so this is the origin of this VH. And another one which is common among Indologists is called the Kyoto Harvard scheme. K is for Kyoto, H is for Harvard. Because the Indologists from Kyoto and the one from Harvard decided to standardize between themselves. Okay, so it's a common way. And the VH is a little bit different, but not that much. So for instance, but these 2 transliteration schemes are preferable in some sense from the information theoretical point of view. So you have, shorter encodings for the computer, these kind of things. The many-1 transliteration schemes, thank you, are somehow preferable for the human. For the humans that know Romanization, okay, that understand this encoding already. because then it's just imitating, like writing a dot under the T is written dot followed by T. See, 2 characters. Okay? Or ri is dot followed by R. Okay? So if you know Romanization, you can read these transliteration schemes, okay? Because if you pronounce them in English, you know, according to the Roman alphabet, it will be very close to the Sanskrit sound. Whereas these 2 schemes are not that good for this purpose, okay? This is a mild way of saying it, okay? So I will abstain. But you see, this is really conventional. I mean, there is nothing deep in that. There is absolutely nothing deep. So this is why in my own system, you know, this heritage site, you have a button where you have the choice between the 4 schemes. So you have a button that says WX, SLP, VH, or KH, okay? So you use whatever is the most convenient for you. The one that has been installed by default is the WX. Okay, so this is why yesterday we had to go through this exercise of spelling WX. Sorry. Okay, so in order to make it easier, we shall not do it anymore. We shall not, spell any transliteration, but on every station in the room, you will have access to this table, yes, which shows the correspondence between Devanagari letters that you know and the various theorists' romanization. And here are the 4 transliteration schemes. Okay? So sometimes they agree, like is A. Okay? And E is E. And U is U. And that's about it. For all the others, you have different variations. And these differentiations are indeed very important. Yes, because remember, these are the phonemes of Sanskrit. So make a mistake of one sound, then you don't get the right result. Okay?